It's a really wonderful opportunity to showcase some of the activities in my team, LSMS. In fact, I will be only partially showing some activities. In fact, I will highlight the work of two current PG students in my lab, Thibaut and Chad, Thibaut Guéquière-Direct and Chad Durussel. Can you say hello? You are in the back. And I want to acknowledge their contributions, and also the contributions of Guillaume Ancio, a long-time collaborator in my team. Say hello, Guillaume. He's been with me for, 18 years, senior scientist in my team. So space under stress, modeling fragmentation from hypervelocity impacts and explosive events. You may find this a bit strange to talk about space in an ENAC research day, but you know there are quite a few of us within ENAC that are affiliated with the EPFL Space Center, and I will showcase some activities, current projects in my team. So we'll be talking about cracks, and you see cracks on this figure. And I will be talking about a huge problem, an increasing problem, that is that we find a lot of strange stuff orbiting the Earth, and the fight for a sustainable planet takes place at ground level, but also for things happening in orbit. So we do find a lot of very useful objects in space, such as operating satellites, but you do find also a lot of junk, and I'm really thankful to Thibaut for this wonderful slide. So you find gloves that have been released by mistake by astronauts, you find toolboxes that are floating around, and this is a problem because we have what we call congested orbits and cascading risks. So, of course, space agencies such as NASA and the European Space Agency, ESA, are keeping track of the largest objects orbiting the Earth. And you have some numbers here, and they are quite worrisome. You see that you have more than 100 million objects that are a size of 1 millimeter and above. And we need to keep track of them because the orbits are congested. And there's no sign of a decrease of this because for two reasons. We have increasing number of stuff we put into space. And for instance, here you see in orange that the number of commercial launches is exploding in recent years. And also, because of these congested orbits, you have collisions, unfortunate collisions. And this creates debris, and you imagine that this is a negative self-feeding loop called the Kessler syndrome. So you may think, who cares about this? Those are small objects, and they cannot create that much damage. Well, I think the ENAC Research Day is a perfect opportunity to recall some basic physics. And if you take a marble of 5 grams, traveling at a speed of 10 kilometers per second, and those are speeds called hypervelocity, speeds of objects navigating around the Earth. Well, that's the same amount of energy at impact of a 1-ton car traveling at a speed of 80 kilometers an hour. So there is a lot of damage upon those collisions. A second topic that interests us, and that's a thesis of Chad Durussel, that's a topic of atmospheric re-entry of vehicles and vehicle demise. Eventually, things are orbiting, and they may come back to the atmosphere. And you want those objects that return to the atmosphere to burn, like shooting stars, and not land on the ground. So we have increasing number of objects that are returning to the Earth. You see statistics from ESA here. Once in a while, unfortunately, the burning process is not very efficient, and you find back the objects in a garden, on a rooftop. This is not great. So we want to understand what happens when objects re-enter the atmosphere. The physics is super complex because you deal with very high pressures, very high temperature. You have thermal ablation. And what we're really up to is try to understand how you can control fragmentation with strategies such as in a fuel tank, detonating the remaining fuel so that you explode the rocket, so that you, as you see in this video from ESA, you do not get one big object returning to planet Earth, but you fragment it into a multitude of little traveling debris to optimize burning efficiency. So super complex problem. Our objective with Chad is to do physics-based simulations of this. We want to do better than the models currently in use in the space agencies because they are limited. They are limited because they are mesh dependent. Mainly, you need to define predefined parts that can detach, but we want a physics to tell you what is fragmenting and where the fragments go. So for this, we want to promote what is called a phase field approach of fracture. I will not discuss this today. I want to say that this is a very, very highly collaborative project. Shad is collaborating with ESA, with scientists in Scotland, and a startup on the EPFL campus called RE-CAE. So all of this was to motivate that we need to account for collisions, explosions, impacts of stuff traveling around the Earth, and we want to get to statistics of fragments that are fully productive and captures right physics. So I already mentioned a couple of times the keyword fragmentation. It's about time that I define it. So what we are up to is to understand high energy events, such as impacts and explosions. Those will create the initiation of a lot of microcracks at a small scale. They will propagate at very, very large speeds. Eventually, they will branch the cracks, and they will form, when they coalesce, will form fragments, little pieces of debris. And at longer time scales, those debris will bounce on one another, and you will also want to understand those repeated contacts. So the problem is highly complex. You want to account for loadings, intense loadings, geometry, structures, material properties, and defects. It's a very dynamic problem, so you have waves, you have inertia coming to the picture, and you need to account for fracture mechanics, crack tips, stabilities or instabilities, and contact and friction between the fragments. And despite of all this complexity, at the end of the day, you want to come up with statistical models that tell you how many fragments you have, what is the distribution of fragment sizes, and of fragment velocities. Okay, so you have at your disposal the three pillars of scientific discovery. I will say that you have a handful of labs around the world that have developed what I call high energy impact experimental facilities. As you can imagine, those are very costly experiments and also very hard to interpret because extremely rapid events with a lot of physics taking place. So about 25 years ago, and I'm aging, about 25 years ago, I took the path of looking at this problem through theory and simulations. So that's what I will present. So I will take you through a brief class so that you learn something out of my presentation. A brief class on the history of work on dynamic fragmentation. So it starts in the 30s, at least from an academic point of view, with publications in the mining industry, road excavation, fuel fragmentation. We have to mention the contribution of the military research, defense industry, and sadly, this is becoming back into focus heavily these days. And here I'm showing the picture of Sir Alan Mott, a Nobel Prize physics winner. And Sir Alan Mott was hired by the British military during the Second World War to work on bombshell fragmentations. You find applications in engineering all over the place, from automotive industry and crash performance, from hydraulic fracturing to medicine with kidney stones fragmentations, all the way to astrophysics. Fragmentation models are used to understand the spread of sizes of galaxies, thinking that they come from a Big Bang, and you want to understand what are the differences in sizes. So typically what you will do, at least historically, you will take a piece of rock, you put explosive, you will smash it to pieces, and then you will measure the fragment masses and come up with fitted functions to describe the distribution of fragment masses. This is me, 20 years ago, a younger version of me, throwing a kitchen plate. See, I was already doing this 20 years ago at Johns Hopkins with my team at the time in the US. Okay. So what do you get from those experiments? You get some observables. Typically, you will find that the fragments follow an exponential or parallel distribution. Sometimes it can be more complicated than this. And here, let me cite the work of Anders Mebon. So who knew that our colleague in ENAC, early in his career, did his first publication, PRL paper in 1996, on composite power laws in shock fragmentation. I knew, and I challenge you to, I will ask you later if you knew about this. So fantastic work. What you also see is that the average fragment size is decreasing with the energy that you give to the system. And that makes a lot of sense. If I take a kitchen plate and I throw it super hard on the floor, I will get a lot more fragments than if I drop it gently, okay? Third, you observe that the fragment velocities go as an inverse power law of their mass, so heavier fragments travel less fast. So all those observations are directly fed into models that are usually empirical or semi-empirical, used by space agencies. Of course, theorists have tried to come up with explanations, rationales behind those observations. So the earliest models were purely geometrical models. And here I'm giving you the simplest example. It's a 1D line, 1936, this paper. And what you do, you're going to take some random cuts, those blue ticks, completely randomly. It's a Poisson process. So there's no mechanics, no interactions between the cuts. And in between those cuts, you find the fragment masses. So because it's a purely random process, you get to distributions of fragments that follow an exponential distribution. But of course, mechanics must matter, otherwise I will not be talking about this. And there we turn back to Mott and his contribution during the Second World War. So Sir Alan Mott had this intuition that things must communicate, there must be interactions between cracks. He assumed in a 1D bar that you get an instantaneous fracture. We will remove this assumption in a minute. And because you make this cut, you get some free surfaces, and this has to release the high stresses in the material. And you will have a region propagating at the speed of sound, which will propagate in blue inside the bar, while the stress will drop to 0. And therefore, in those blue regions, you are not allowed anymore to make a cut. They are protected. Okay? So cracks interact via elastic waves, and this has an influence. We jump to the 1980s, and the very, very used, even today, in design codes, what are called the energy models. And here I'm showing the model of Grady in 1982. So it's a beautiful model, extremely clear paper, one line of mathematical derivation. Still a 1D problem. We are taking this bar and we are stretching it. On the right, I pull with plus V. On the left, I pull with minus V. So I'm stretching the bar. That gives me what we call local kinetic energy, not global kinetic energy, because if this bar would be moving as a rigid body, I have no energy to stretch it. So I must stretch it, and it's the slope of velocity that matters. So I'm taking this local kinetic energy, and I'm saying I'm going to use it to form new cracks. This has a cost. Think of surface energy. And just by equating those two terms, as I said in one line of derivation, you come with a prediction of a fragment size S that scales with the price to pay to create cracks. That's this quantity GC. And it scales with the strand rate, the loading rate epsilon dot, to the power minus 2/3. So a very beautiful model that's usable in design codes. Of course, it has limitations. You see that all my fragments have the same size, S, but when I drop a kitchen plate, I have large and small fragments, and that turns out to be important. Okay, so my work in this field started about 20 years ago with a simple idea of what we call the Mott benchmark problem. Very simple geometry. It's a ring, a one-dimensional ring that we force into radial expansion. We make it grow radially. And therefore, as we stretch it, the stress in a bar will increase with time up to peak strength, at which point you reach the material strength and will start to introduce cracks, will break the material. Those are the little red explosions. I'm introducing cracks, and once I introduce a crack, we will remove the assumption of MOT that fracture is instantaneous, but we'll follow the principles of fracture mechanics, and we say the stress carried by those little cracks that we introduce is gradually going down to zero as a function of the opening displacement. This is called cohesive fracture. And that gives you a time scale of the process. Of course, because we are doing this numerical benchmark, we're able also to model the waves traveling around the circumference of the ring, and there will be communication taking place. And there are things we understand very, very well with this process. We understand how the stress drops. You trap elastic waves. We understand how many fragments we form as function of material properties and loading properties. We understand fully the convergence of the problem, how much computational power we must use to get to a solution. So we have a good handle of distribution of fragment sizes, and including as function of defects and material parameters. But there are things we do not understand well. Those are complex structures that add up flexural waves on top of this. We do not understand also composite materials, and we do not have a good understanding of fragment velocities. This remains very, very empirical. For what we understand well, we can come up with very simple scaling laws that extend the theory of Mott and Grady. And here we're looking at the fragment size as a function of strand rate. You recognize the model of Grady. It's a log-log plot. So this straight line has a slope of minus 2/3. Larger strand rate gives you smaller fragments. We recover this. We see that we get, with our data, that's this red line, we have the same slope, minus 2/3. But we do have smaller fragments. And this is because we show that secondary fragmentation matters. When fragments bump onto one another, we have a mechanism to convert global kinetic energy into local kinetic energy. So this is why we get smaller fragments. You also notice that we have a lot of points around this fitting curve, and those points are a vast parametric space. But because we understand the role of properties, we can make those axes non-dimensional using material properties so that our data is collapsing. So we have now usable models for design codes, which actually use in some design codes. Okay? So over the years, at EPFL, we have spent a lot of time and resources to scale up this benchmark problem to more complex geometries and higher dimensional problems, such as an exploding sphere, tempered glass fragmentation. And for this, we need to have really high-performance computing code and scalable software. And here we're using Akon2. It's not the only software we developed in a team. We have here a bunch of logos. I want to acknowledge the work of Guillaume Anciot and Nicolas Richard that over 15 years or more have developed open source software that we make available to the community. Akon2 is one of them. And in fact, this software Akon2 that some of you are using on campus and beyond has unique features. It's the only software, worldwide, commercial or academic, that gives you the ability to model explosions with complex topological changes in a mesh. So please connect to this open source initiative if you want to learn more about this, or come talk to us. I will conclude my talk by mentioning the CLIP project. This is an ongoing collaboration between a group in France, the team of Nicolas Moès, financed by ANR, and the Swiss National Science Foundation, and it's the work of Thibault. And this CLIP is an open source initiative that promotes a new method to model cracks. I will not go into details of this, but the end goal is to come up with a statistical open source database of impact and explosions of complex structures. So the topic is extremely challenging because we have two timescales we need to deal with. We need to model the short timescales of microcracks initiation, crack propagation, but also the very long timescale, relatively longer, of impacts colliding with one another within a structure. And this is why there's so little work done on distribution of fragment velocities, because you need to capture those long time scales. And I want to highlight that there's a huge challenge that Thibault is addressing this year, in fact, in his research. And I won't give you much details about this, but that has to do with the very non-smooth nature of the contact algorithms. And I know that we'll say something to Catherine. So when you fragment a piece of material, you see here an example of lots of cracks. You have also a lot of trapped elastic webs, fragments vibrate. And you keep switching from a tensile part of a region which is damaging to the contact part from which it's being compressed. And you see that in this model, between tension and compression, you have a change of slope. You have a discontinuous slope of the slope. That's what we mean by non-smooth. And with this non-smooth problem that we deal with, well, we don't preserve perfectly well the energy. So if you look at short time scales, and you follow the number of fragments as a function of time, you think you are reaching a plateau, and that things are well in control. But this little addition of energy, gradual addition of energy, eventually that leads to a huge instability and an explosion of the number of fragments, which of course is not physical. This is completely numerical. So Thibault is collaborating with Vincent Incari in Grenoble, an applied mathematician, on non-smooth integrators that preserve the impulse. If you're interested in this, please go talk to Thibault, and that will give account to some unique capabilities to get to fragment velocities finally. So with that, let me give you some takeaways and next steps. I did spend quite a bit of time motivating that we are confronting a huge problem that will get worse and worse. Congested orbits, so be ready to hear in the news more and more stories of damage to the space station or to operating satellites. You see that with the extrapolated traffic as a function of the year, you see that the cumulative number of catastrophic collisions is exploding. So we need reliable statistics, physics-based model to predict better our tracking of debris and the risks based on some specific orbits that of the new launches that we'll put into space. Archon2 is a good tool for this. In fact, I would say it's a unique tool with unique capabilities for dynamic fragmentation. But of course, we need to make it better, especially for this question of stability for long time scales. With that, I only reflected part of the activities of the team. We have a larger team that has a wide range of interest, including rheology, wear, friction, earthquake physics, data-driven mechanics, concrete ASR damage in concrete, so on and so forth. I want to thank the whole team for their great contributions. We have a fantastic atmosphere. And with that, I will be happy to take your questions. Thank you for your attention, if time permits.